Sorry about that. I don't know what's going on with the microphone, but I think it's working now. So hopefully. Um, Yesterday we talked about energy diagrams and how to use those to talk about the change in energy in chemical equations. Today we are going to talk about another factor that we can measure in chemical equations, and it's called entropy. So not enthalpy like we've been talking about, but entropy. And I'm on page 471, and it's towards the top in blue, entropy. And entropy is a measure of the disorder that exists in any system. So first of all, let's talk about the units before we kind of talk more in detail about what it is. So the units is going to be an energy unit divided by moles and Kelvin. So you have either joules or kilocalories or kilojoules or calories divided by moles times Kelvin. All of those are acceptable units for entropy. And entropy is abbreviated with a capital S. So like we had enthalpy with a capital H, entropy will be a capital S. Don't ask me where they get these letters from because I don't know. So yes, it might seem kind of weird that we can measure disorder in a system, but let's just talk about a random example. So let's think about, okay, I'm going to just read it to you because it sounds better the way they say it. For example, suppose a priceless vase is on a shelf somewhere and something causes the vase to fall onto the floor and shatter into a million pieces. Which situation do you think represents more disorder? Clearly, when the vase is shattered, it's more disordered than when it was sitting on the shelf in one piece. While the vase is sitting on the shelf, it is in a state of low entropy because it's not very disordered at that point. However, when the vase shatters, it moves into a state of high entropy. I hope you guys can hear me okay. I just realized I'm on the wrong internet. So we'll see how it goes. But yes, when it shatters, it's in a state of high entropy because it's very disordered when it shatters. There is a visual for you at the bottom of page 471, figure 13.3. It shows a marketplace at low entropy. Everything is organized in its place. And then it shows the marketplace at high entropy. There's boxes and trash thrown everywhere and everything's all jumbled up and in a mess. So kind of just to get in your mind the difference between high entropy and low entropy. So highly disordered and versus not very disordered at all. Okay, so let's think for a minute if we can imagine the reverse process happening. So can we ever imagine the vase is on the floor in a million pieces and then spontaneously it rearranges itself into a whole vase again? No, we can't, because this can't happen. But the reason it can't happen is because of the second law of thermodynamics. And that is on the top of page 472, if you're following along. So the second law of thermodynamics says the entropy of the universe must always either increase or remain the same. It can never decrease. So if you think about that with the vase, you can't go from a state of high entropy to a state of low entropy. So it can't go from highly disordered and shattered to put back together again. It would be going from high to low. So the way that entropy has to be dealt with in the universe is it always increases. So more disorder, never less. Or either it stays the same, but never ever less disorder. That's why broken things don't spontaneously fix themselves. All right, so this helps us to determine what kind of events are possible in nature and what kind of events are not possible in nature. That's why it's important to science. Okay, so entropy, the measure of the disorder in a system. So you have to make sure you're really comfortable in determining whether a given state represents high entropy or low entropy. So we're going to talk about 3 different things that affect entropy in chemical equations. So the first and foremost, the entropy of a substance changes when the substance changes phases. So we have solid, liquid, gas, aqueous. And in the solid phase, atoms that make up the substance are held in place, and they're only allowed to vibrate so small that you can't even see it. So since the molecules cannot move around very much, they're not very disordered at all. So that means that the solid state has the lowest amount of entropy. So if there's a substance, for example, water, in its solid state, and as ice is in its lowest state of entropy because it's barely moving at all. You can't even see it. So as you would think, as substances move to liquids, they have a little bit of a higher level of entropy. And then the gaseous state has the highest level of entropy or disorder, because think about it, the molecules are all moving around so fast, they're bumping into each other, they take up the most space, they're just colliding. That's the highest state of disorder for a substance. So gas, highest entropy; solid, lowest entropy. And that's in blue there on page 472 for you. The second thing we'll talk about is temperature. So as temperature increases, so does entropy. So that should also make sense to you, because the hotter molecules get, the faster they're moving. So if they're moving faster, they're going to become more disordered versus if they're just barely moving at all. So higher temperature, higher entropy; lower temperature, lower entropy. So the entropy of a system increases with increasing temperature. Let's see. Okay. So they did point out, which I thought was good, if you have two identical samples of matter, so say you have 2 glasses of water, and you raise one's temperature, then the sample with the higher temperature is going to be more disordered. So say boiling water versus room temperature water, if that makes sense. All right. Finally, the third thing is the more matter there is in a system, then the more disordered it is. And this should make sense if you think about, for example, your own room. So think about if you only have a few things in your room, it looks nice, neat, tidy, orderly. But think about if you have a ton of junk in your room and a bunch of stuff just cluttering it up, obviously it's going to be more disordered. So same thing works in science. The entropy of a system increases as the matter it contains increases. So more matter, higher entropy; less matter, lower entropy. All right, so for example, a sample that has 5 moles has more entropy than a sample of the same gas that would contain only 3 moles. So more matter, higher entropy; less matter, lower entropy. Okay, so chemists usually are more interested in the change in entropy that a system undergoes. So rather than just how much disorder it has, maybe how much disorder it starts with in a chemical equation and how much it ends with, and how that varies. Same thing that we've been doing with energy, with enthalpy. So this should be pretty familiar to you. There's an equation there on the middle of page 473, and it is the change in entropy of the universe will be greater or equal to 0. So remember, we talked about how it's never going to decrease. You're never going to become less disordered, like things aren't going to just spontaneously be put back together if they're broken. That's what that's saying. So entropy is always either increasing or staying equal to 0. It can't go negative. So always higher. So there's that equation for you. And there's 2 ways that we can determine the change in entropy. The first is a qualitative method. This just allows us to determine the sign, so either positive or negative, of the change in entropy of a chemical reaction. So we'll kind of talk about that method briefly. So first, all we have to do is look at the number of molecules on each side of the equation. So you're going to use those stoichiometric coefficients, because that's going to tell you how many moles you have of each substance, right? And we're also going to look at the phase of the substances involved, because we talked about how phase affects entropy and makes it higher or lower. And let's see. So in general, the side of the reaction that has the most molecules in the gas phase has the highest entropy. If no gases are present, then the side that has the most molecules in the liquid or aqueous phase has the highest entropy. And finally, if all substances in the chemical equation are solids, then the side with the largest number of molecules has the highest entropy. If none of these situations is true, then we just can't determine the sign of change in entropy this way. So hopefully that's not confusing, but we're going to run through an example just to kind of talk about it. So example 13.6 at the bottom of 473. We're going to determine the sign for the change in entropy for this equation. And you'll see it there. It says letter A, and it starts with zinc. So we've got a solid zinc plus hydrochloric solution that's aqueous. And on the other side, we have one aqueous solution and one gaseous solution. Sorry. There's 1 mole of each substance here. There's no coefficients. So that means we have a solid and an aqueous, and we have an aqueous and a gas. So which side do you think is going to have higher state of entropy? The right side would, because it has 1 in the gas phase, and the reactants don't have any in the gas phase. So this means that the change in entropy is positive. So if the reactants have a lower entropy and the products have a higher entropy, that's when it's positive. Now, if you start with your reactants having a higher state of entropy and the products end with a lower entropy, it's going to be negative. All right, so let's look at letter B. Letter B there on the top of 474, we have nitrogen gas. We have 3 moles of hydrogen gas. And on the right side, we have 2 moles of NH3 gas. So that means we have 4 moles total of gas on the left because we have 1 N2 and 3 H2. Whereas in the products, we only have 2 moles of gas. So which side would have a higher state of entropy? The reactant side, the one with 4 moles, because they're all gases. So now we're looking at the number. So we have 4 moles on the left, 2 moles on the right. So that means it's going from a high state of entropy to a lower state of entropy, which means the sign would be negative. All right, last one, letter C. Looks like we have 2 moles of a solid plus 1 mole of a solid. Okay, so we have 3 moles of solids on the left. Now let's look at the right side. We have 1 mole of aqueous, 2 moles of aqueous, and 8 moles of a liquid. So definitely the right side has a higher state of entropy. Not only does it have more moles, but it has liquids and aqueous phases versus the solid phase. So we're going from a low state of entropy to a higher state of entropy. That means our sign is positive. Okay, so we are going to do some on our own. We are going to do 13.9 in your book, in your student book. So if you'll get that out with me. All right. We're determining the sign for the change in entropy for these reactions here. So let's look at letter A, 13.9. All right, so first on the reactant side, we have 1 mole of an aqueous solution, 1 mole of a liquid, and 1 mole of a gas. Now on the product side, we have 1 mole of aqueous and 1 mole of solid. So I have 3 moles on this side, 2 moles on this side. I have a liquid, a gas, and an aqueous, and I have an aqueous and a solid. So the reactant side is going to have more molecules, and it's going to have molecules in a phase with higher states of entropy. So that means we're going from a high state of entropy to a lower state of entropy, which means our sign is going to be negative. So the answer there would be negative for A. All right, for B, we have 2 moles of a gas and then 1 more mole of a gas. So we have 3 moles of gas. And then on the product side, we have 2 H2O2, which means we have 2 moles of a gas. So 3 moles of a gas versus 2 moles of a gas. The reactant side is higher, the product side is lower. So that means that the sign will be negative. All right, last one, letter C. We have there 2AgOH, so that's 2 moles of a solid. It tells you it's in the solid phase. And then we have 1 mole of an aqueous. And then on the product side, we have 2 moles of an aqueous and 1 mole of an aqueous, all right? So since we have 3 in the aqueous phase on the product side and 2 in the solid phase, and then 1 in the aqueous phase on the reactant side, then that means the products are going to have a higher state of entropy because of their phase. So that means we're going from a lower state of entropy to a higher state of entropy, so our sign is going to be positive. So the answer for C is going to be positive. Hopefully that made sense to you. If you need help further, just let me know. Okay, so let's see. There is a way to determine the actual number though, not just the sign, so we're going to talk about that. There's a table there on page 475. It's table 13.4, and it has some absolute entropies for some of the substances that we talked about in table 13.3. So these are substances we've already been using with the other equation that we learned earlier this module. And you'll use an equation that's also very similar to equation 13.3. And you'll see it there at the bottom of page 474. It's equation 13.5. And it says that the change in entropy, I might write it out for you, even though you're probably following along. Okay. The change in entropy, which remember we said was S. Oops. This thing is so annoying sometimes. Okay, the change in entropy, remember what this means? That means standard conditions, okay, is equal to the summation, try to draw that, of the standard entropy of the products. I'm just going to put P for products, minus the summation of the standard entropy of your reactants. So very similar to the last equation that we used, you are going to add up all of the standard entropies for your products, and then you're going to subtract all of the sum of your standard entropies for your reactants, and that's going to give you your change in entropy. Okay, let me get out of here for just a second. Sorry. Okay, so the one difference that you need to know when you calculate the change in entropy, remember when we talked about change in enthalpy and we said that for elements it was 0? Well, for change in entropy, the entropy of an element is not 0. All substances, even elements, have an absolute entropy. So they all have some degree of disorder to them already. So they'll never ever be zeros here like there were in the last equation. Okay, so let's see. All of the entropies listed in that table on 475 at the top are positive. This is because the table does not contain values of change in entropy. It's just containing values of entropy. So these are not changes in entropy. This is simply the value of the entropy of each substance listed there. And like we said, all substances have some level of disorder. That's why they're all positive. Also, another thing to notice is the unit. The unit is joules divided by moles times Kelvin. And when we talked about enthalpy, we were dealing with kilojoules. So what that is basically saying here is that the numbers on this table are about 1,000 times smaller than the ones on the table 13.3. Just something to think about. It's kind of interesting. So remember, let's see. Okay, they're not going to give you an example. They just want us to try it on your own because it's so similar to that other equation that we did before. So we're going to go ahead and do on your own 13.10, and after that, we'll be done. Okay, so on your own 13.10, and I'll do it on here for you. Hopefully you're following along. Okay, I'm going to clear this. Oh, I'm wondering if I should. I'm just going to leave it for right now because we'll be using this. Okay. All right. So they're giving us an equation. on your own, 13.10. And they're giving us CaO in a solid phase plus CO2 in the gas phase. I'm going to put equals, but you know that's just your arrow. CaCO3 in the solid phase. Okay, so this is our equation that we're looking at. What we're going to do is use this equation that we just learned to calculate the change in enthalpy. Okay, so first, let's just start plugging in. All right, so I'm using this equation, so I'm going to say change in S is equal to, so I'm just using this right here, the change in entropy is equal to the sum, so let me do a bracket, of my reactants here, my product, which I only have one of. So I'm looking on table 13.4 for the value of entropy for CaCO3 in the solid form. So CaCO3 in the solid form, that's going to be 5 columns over, and the value there is 92.9. Now I'm looking here, I don't have any coefficients, so technically it's just 1 mole of this. So you can write 1 mole times the value there is 92.9, and this is technically what you should do, but usually when it's 1, I just don't even write it because it's not going to change my value. And that's joules divided by moles times Kelvin. Okay, so that's my product there, the summation. And all of that minus, now I need a new bracket. Let's do our first substance. Our first substance is CaO in the solid form. So I'm just adding up the reactants here. So let's look at the table for CaO in the solid form. That's going to be in your third column over. And it is 38.2. And again, there's just 1 mole. I'm going to write it out, but you don't necessarily have to when it's 1. But it's not a bad practice to get used to, because say there was a coefficient of 2 here, I'm going to need to put 2 moles times the value. But I'm just going to put 1 because there's no coefficient. So 1 mole times the value is 38.2. Okay, and then we need to add our other reactant here, CO2 gas. So let's look at the table for CO2 gas. That's right above CaO in the solid form. And again, I have 1 mole of it because there's no coefficient there. So 1 mole times the value is 214. I didn't put the other units, sorry, let's fill those in. Joules divided by moles times Kelvin. Okay, and I'm going to close my parentheses and close my bracket because that is both of my reactants. So I have the product minus all of the reactants added together. Now, let's kind of clear some of this out of the way since we know what it is now, so that you can see the answer. No, no, no. This is so irritating. Sorry, guys. I'm thinking about leaving this dot. Okay, I'm just going to leave the dot. Okay, so we're going to plug it in the calculator and then find out what we get. So when you plug it in the calculator, would you like me to type out what you're going to put? I know sometimes y'all struggle with that, so let me write that. It's ones. You really don't need to plug the ones in, but for practice, we'll go ahead and do it. So you're going to do parentheses, 1 times 92.9, close parentheses, close parentheses. I guess you technically only need 1 set because there's only 1 product. Minus all of that, minus, now we need 2 sets of parentheses because we've got 2 things here. We've got 1 times 38.2, close your parentheses, plus Open a new set of parentheses, 1 times 214. Close that parentheses and close that second parentheses. So all of this is in parentheses together because the reactants are being added up. All right, once you put that in your calculator, you will get negative 159.3. Now notice here your moles are going to cancel because you've got moles here and moles here. So you're going to be left with joules divided by kelvins. That's going to be your unit. Joules divided by Kelvin. All right, let's look at significant figures. Here we have 3, 3, and 3. So we really need to go to 3. So let's do negative 159 joules divided by Kelvin. And that is your answer. And that was all we had for today. I was just looking at tomorrow's. We're going to finish up the module tomorrow. If you have any questions on what we talked about since no one was here, just let me know. But yeah, we're going to finish the module tomorrow. And then for homework, I'm just going to have you go ahead and do the test. I'll be here available if you need help. I always am. If you guys want to ask me any questions about the test, you can feel free to use your book and your notes. Just don't use the internet, please, for your test. And I'm trying to think if there's anything else. If you're going ahead, 13 on your own, 13.11 has an error in it, so you might want to just wait till tomorrow on that one. And I think that's all I had for today. So reach out to me if you have questions, need help. I'm here. We only have a couple weeks of school left, so I'm super excited. We're almost done, and y'all are doing good to be on quarantine and doing all this on your own. So I'm proud of you guys. Keep it up. Let me know again if you need help, and hopefully I will see everybody tomorrow. Bye.